Mm. Once again, I will start with the comparison between Brayton and Otto cycle. The Brayton cycle and Otto cycle, the PV diagram as shown in figure here. Okay, PV and TS diagram. That Otto cycle you can call it a constant volume cycle. Okay, that curve which will be representing here 1, 2, 3, 4, 1. Okay, this is in the PV diagram. I am representing here the PV diagram. That is what 1, 2, 3, 4, 1. That is what constant volume cycle. That is what once again I can recall this area of 1, 2, 3 dash 4 dash 1. This is I can call as a Brayton cycle in the PV diagram. Similar way for the TS diagram, that is what 1, 2, 3, 4. That is what Otto cycle. That is a constant volume cycle. Then 1, 2, 3 dash and 4 dash. This is you can call as a Brayton cycle. The area representing for Brayton cycle. This is the PV and TS diagram of Brayton and Otto cycle. Then the comparison. What are the differentiate between existing of differences which will be existing between the Brayton and Otto cycle? For the same compression ratio and work capacity, the Brayton cycle which will be handles larger volume and smaller range of pressure and temperature than Otto cycle. The same compression ratio and work capacity, Brayton cycle handles larger range of volume and smaller range of pressure and temperature than Otto cycle. Okay, then because of that one in the reciprocating engine field, Brayton cycle is not suitable. Because of that one, it will be because of large volume flow rate and also with the minimum pressure and temperature with respect to the Otto cycle. Compared with the Otto cycle, the reciprocating engine Brayton reciprocating engine field, Brayton cycle is not suitable. A reciprocating engine cannot efficiently handle the larger volume flow and low pressure gas, for which engine size become large and friction loss also become more, so that the Otto cycle is suitable for reciprocating engine field. That means what I am telling is it will be operating in the same compression ratio and work capacity. Brayton cycle larger range of volume and smaller range of pressure and temperature than Otto cycle, so that reciprocating engine for the Brayton cycle is not suitable when it will be compared to the Otto cycle. Then another one differences, the comparison between Otto and diesel cycle, Otto and the Brayton cycle, the turbine plants, the Brayton cycle is more suitable than Otto cycle. In the turbine plant, in the turbine, in that Brayton cycle is more suitable than Otto cycle. These are the three differences which will be existing in the Brayton and Otto cycle. It will be working on the same compression ratio and work capacity. Brayton cycle it will be larger volume and smaller range of pressure and temperature than Otto cycle. So that the reciprocating engine flow Brayton cycle is not suitable than Otto cycle. In turbine plant, Brayton cycle is more suitable than Otto cycle. These are the differences in the comparison between Brayton and Otto cycle. Then another one important thing here, the methods to improve the performance of simple gas turbine. Methods to improve the simple gas turbine. Here the three different method is there. That is your regenerative gas turbine, reheating gas turbine, and intercooling gas turbine. Based on the three different method to improve the performance of simple gas turbine. Okay, first one I will discussing about the regenerative gas turbine. The name indicates here the regenerate. The regenerate. What is the amount of that heat will be liberated? That once again it will be regeneration which will be taken place in the regenerator. This is you can call a regenerative gas turbine. The efficiency of the Brayton cycle can be increased by utilizing part of energy that of exhaust from the turbine in heating up in the regenerator. That is a heat exchanger called a regenerator, thereby reducing the amount of heat supplied to the external amount supplied to the external source also it will be reduced as the minimum amount of heat supplied, maximum amount of work will be generated. This is what it will be existing in the regenerative gas turbine. In the regenerative gas turbine, it will be consisting of compressor, regenerator, and combustion chamber and turbine. Here the exhaust of this gas is once again which will be reheated. The compressed air which will be coming from the compressor, which will be reheated. The preheated will be taken place here. The preheated air once again passed to the combustion chamber. Here amount of adding heat to the combustion chamber, it will be reduces. Minimum amount of heat which will be supplied to the combustion chamber, which will be getting a maximum power output. This is what the working principle behind the regenerative gas turbine. Very simple is that the mechanism is very simple in the regenerative gas turbine. That what is the exhaust gas? Once that exhaust gas which will be contain some amount of heat, that heat is utilized for air which will be entering into the combustion chamber. The preheating of the air which will be entering into the combustion chamber, it will be taken place. In that way the amount of heat added to the combustion chamber, it will be reduced as that is what minimum amount of air which will be entering into the combustion chamber, it will be gives the maximum work output. So this is the one way of improving the efficiency, to improve the efficiency of the gas turbine. This is what regenerative gas turbine. This is what the TS diagram of the 1 to 2, 3 and 4. Okay, here what about the temperature is there? That is white is also equal to the T2 temperature. What is the leaving from the exhaust gas leaving from the regenerator is also equal to the air which will be entering into the combustion chamber. That is what regenerator. Before entering to the combustion chamber, so the regenerator is there. That is we can call it a heat exchanger. Okay, this is also equal. Then Tx is equal to T4. What is the amount of heat is leaving to the atmosphere? That is, it will be leaving to the exhaust gas. Once again pass it to the exchanger. That is what T4 is equal to Tx. Like that only you should write down the regenerative gas turbine TS diagram. Then I will write down here that is the efficiency, the thermal efficiency. Okay, WT minus WC divided by WT. What turbine work minus compressor work divided by turbine work. Okay, then I'll write down here Cp into T3 minus T4 minus Cp into T2 minus T1, then Cp into T3 minus T4. These things are cancelled. What is the remaining term? 1 minus T2 divided by T1 divided by T3 minus T4. In this, we have to take a T1 is a common term here. T2 divided by T1 minus 1. Here, the T3 we have to take into the common term is becomes 1 minus T4 divided by T3. That will be gives T1 divided by T3. It becomes T3 divided by T1. You can call as what? Small t. That is, you can call the temperature ratio. Here, T1 divided by T3 is there. That becomes 1 divided by T. 1 minus 1 divided by T into the R to the power of gamma minus 1 divided by gamma minus 1. 1 minus 1 divided by R to the power of gamma minus 1 divided by gamma. How to write this gamma? Here R here, that is based on the process 1 to 2 and 3 to 4. That is the isentropic compression process, isentropic expansion process based on the temperature and pressure relationship. That is what T2 divided by T1 is equal to P2 divided by P1 to the power of gamma minus 1 divided by gamma is also equal to the R. That is, you can call it the pressure ratio. R to the power of gamma minus 1 divided by gamma. Then the expansion process 3 to 4. T3 divided by T4 is equal to P3 divided by P4 to the power of gamma minus 1 divided by gamma is equal to the R to the power of gamma minus 1 divided by gamma. Then you should write down here. This is what the expression 1 minus 1 divided by T into R. That is what T2 divided by T1, it becomes R to the power of gamma minus 1 divided by gamma minus 1. Here T4 divided by T3 is there. Here T3 divided by T1. That means 1 divided by R to the power of gamma minus 1 divided by gamma. Then you can take LCM here, that it becomes the thermal efficiency of the regenerative gas turbine. It becomes 1 minus R to the power of gamma minus 1 divided by small t. Small t can call it temperature ratio. It gives T3 divided by T1. That is a temperature ratio. This is very, very important relationship and expression. Okay, very simple derivation is there. Okay, that is what regenerative gas turbine. Okay, then go to the next one, that is you can call the reheating gas turbine. The gas turbine cycle with reheating and multi-stage expansion. While reheating gas turbine, that will be taken place reheat the two times it will be heated up this gas, that is you can call the reheating of gas turbine. Here in the reheating of gas turbine, it will be consisting of high pressure turbine and low pressure turbine. It will be consisting of compressor, high pressure turbine and low pressure turbine. All these compressor and turbines are connected with a single shaft. All the shafts will be interconnected one by one. Okay, now at 1 to 2, the air which will be admitted to the compressor, the highly compressed air which will pass to the combustion chamber. Here what happens, enormous amount of heat energy which will be liberated, that will be expanded in the high pressure turbine. Then that it will be living into the reheat, it will be exhaust. Once again, that heat, once again, it will be passed to the reheater. Then once again, they heated up this reheater to the initial, that is what T2. What is the amount of temperature is there? In the same amount, the temperature will be reached it here. That is a the reheater. Once again, the expansion process will be taken place in the low pressure turbine. Then that exhaust will be taken place through a 6 to 1. Once again, the condenser is there. Heat rejection process will be taken place. That is the initial temperature will be given to the heat rejection, means that heat is leaving from the condenser. Then the cooled air once again passed to the compressor. The cycle which will be repeats here. This is what reheating gas turbine. In the reheating gas turbine, you should remember it. It should be consisting of two turbines, that is high pressure turbine and low pressure turbine. Why I am telling is because we are solving a problem on these conditions. So that's why this is very, very important here. While writing the black diagram, you should remember it while drawing the PV and TS diagram. Then I'll write down here how to write the PV and TS diagram here. 1 to 2, isentropic compression process. Then 2 to 3, heat addition process, constant pressure heat addition process. Just you can observe here in the PV diagram, the 2 to 3 is constant pressure. The constant pressure heat addition process, the temperature will be increases here. Then once again 3 to 4, the expansion process will be taken place. Once again, that heated up this exhaust gas leaving from the high pressure turbine to the 5, that 0.5, that means what, T3 is also equal to the T5. Then the expansion process will be taken place T5 to T6. Then 6 to 1, once again the cycle which will be repeats here, when the heat rejection process will be taken place in the 6 to 1. That is what I have written it. 1 to 2, isentropic compression. 2 to 3, constant pressure heat addition process. 3 to 4, the expansion process. 4 to 5, once again the constant pressure heat addition process. Then 5 to 6, once again the expansion process will be taken place. Then 6 to 1, heat rejection process, constant pressure heat rejection process. In this way we have to write down. Okay, here while writing the TS diagram, T3 is equal to T5, like that only you should write down. Then T4 is equal to T6, like that you should write down. The proper sketch of TS diagram is very important while trying the reheating of gas turbine. Okay, P2 is equal to P3 here. P4 is equal to P5. P1 is equal to P6. Okay, all the relationship we are taking into account while derive the expression. So that's why I am telling you should write down the proper PV and TS diagram. While reheating means you should consider the two turbines which will be existing, that is a high pressure turbine and low pressure turbine. The two stages, the expansion process will be taken place here. That is very important thing while improving the efficiency of the simple gas turbine. Okay, now how to derive the expression for the simple gas turbine. Okay, now capital R, that is you can call the pressure ratio, that is isentropic compression process. That is what P2 divided by P1, the same compression ratio. Then R1 is equal to that is what R1 P3 divided by P4, that is the expansion process. Then R2 P5 divided by P6. Then small t, T3 divided by T1, the maximum temperature ratio. This is what R1 into R2, that is what P3 divided by P4 into P5 divided by pieces. Based on the PV diagram, P4 is equal to P5. Then R1 into R2 is also equal to the R. It becomes P2 divided by P1. Just what is the value you are getting? That P5 is equal to P4, P3 is equal to P2, P6 is equal to P1. That means it becomes R1 into R2 is equal to the P2 divided by P1 is also equal to the R. That is, you can call the isentropic compression ratio. That is what? Adiabatic compression ratio. This is what the simple expression behind behind this is what reheating gas turbine. Then once again we'll be move on to the last one is gas turbine cycle with multi-stage compression with a perfect intercooling. Okay, in the multi-stage compression means we have to existing the two compressor. The first one is low pressure compressor, another one is what? High pressure compressor. The gas turbine cycle with multi-stage compression process with the intercooling, in between will be having a intercooler is there. Otherwise it will be the high pressure which will be existing. Due to that high pressure, it will be damaged to the whole system, which will be the collapse. So that's why we have to need a intercooler is there. In the multi-stage compression process, it will be existing two compressors and one turbine. That is a expansion process, single expansion process, but here multi-stage compression process. The compressors which will be and the turbine mounted on the same shaft. What is the amount the power will be generated? The part of power it utilize it for run the compressors. Then once again, that is a process 1 to 2 isentropic compression process in the low pressure turbine. After compressed air which will pass it to the intercooler, that heat will be rejected. Then once again the rejected heat which will be rejected heat and to the atmosphere, then that is a cooled air once again passed to the high pressure compressor. Then will be once again compression process will be taken place here. Then compressed air once again passed to the combustion chamber. Here that enormous amount of heat energy will be liberated. Then which will pass it to the turbine. The expansion process will be taken place. The rotation of the turbine will be existing. Due to the rotation of the turbine, the power will be generated. The work which will be executed. Then the exhaust gas once again pass it to the compressor through a condenser. Here the condenser, the cooling effect will be produced. The rejection of it will be taken place. Once again, the temperature will become the atmospheric temperature of air once again pass it to the compressor. Similar way, the continuous process will be taken place here. Then I will write down the TS and PV diagram. That is very, very important once again here. That is what 1 to 2 in the PV diagram. What I am telling in the PV diagram, 1 to 2, that is what isentropic compression process. Isentropic compression process. Then 2 to 3, the heat rejection. 2 to 3 constant pressure heat rejection process will be taken place. 2 to 3 constant pressure heat rejection process. Okay, then in the heat rejection process will be taken place. What is the amount of air which will be entering to the low pressure compressor? T1 is equal to T3. Like that only we have to write down in the TS diagram. That is very, very important thing here. We have to write down the compressor, the temperature at the initial condition. Air which will be entering into the low pressure compressor is also equal to the T3. Like that, the heat rejection process will be taken place in the intercooler in between low pressure turbine and high pressure low pressure compressor and high pressure compressor. Then once again the compressed air once again passed to the combustion chamber 3 to 4 high. Once again the isentropic compression will be taken place in the high pressure compressor. Then 4 to 5 that combustion 4 to 5 constant pressure heat addition process will be taken place. Constant pressure heat addition process will be taken place. Then 5 to 6 once again the expansion process. 5 to 6 once again isentropic expansion process. The turbine, the work will be generated. Then 6 to 1 once again the heat rejection of the passed through a condenser. Once again the air which will be exhaust air it will be recycled to the low pressure compressor through a condenser. In the condenser the heat rejection process will be taken place. The cooled air once again passed to the low pressure compressor. This is the way of the working principle behind the gas turbine cycle multi-stage compressor. Multi-stage compressor. This is very, very important while drawing the TS and PV diagram. Here in the PV diagram, P1 is equal to P6, P3 is equal to P2, P4 is equal to P5. Like that only we have to write down the PV diagram. That is very, very important. In the TS diagram, the T1 is equal to T3 because of intercooler is there. Once again, bring back to the initial temperature. Then T4 is equal to T2. Like that only you should write down the TS diagram. Then afterwards, we have to derive the expression for a compression ratio. That R1 is equal to P2 divided by P1. Here that low pressure compressor process, the pressure ratio. Then high pressure compressor pressure ratio. That is what R2 is equal to P4 divided by P3. It becomes capital R is equal to P5 divided by P6. That is the expansion process. The maximum work output R1 is equal to R2 is equal to root of R. This is what the maximum work output through a multi-stage compression process. Okay, here the low pressure compressor pressure ratio. Here the R2 is a high pressure compressor pressure ratio. That is capital R is equal to expansion process. That is a P5 divided by P6. Okay, then this is all about multi-stage compression process. Okay, this is the method of to improve the efficiency of the gas turbine. First one is what? Reheating. Second one is what? First one is what? Regenerator. Second one is what? Regenerative and multi-stage compression process. Like that, it will be having a three different method to improve the efficiency of the gas turbine. Now we can solve a problem on gas turbine. Okay, now we read out the problem here. This first, the simple problem on gas turbine. A simple gas turbine plant operating on Brayton cycle as air entering the compressor at 100 kilopascal and 27 degrees centigrade. The pressure ratio is 9 and the maximum cycle temperature is 727 degrees centigrade. What will be the percentage change in cycle efficiency and the net work output if the expansion in the turbine is divided into two stages of each pressure ratio is 3 with intermediate reheating to 727 degrees centigrade? Assume compression and expansion are ideal isentropic. Okay, here the two here in this problem we have to solve based on the data. We have to solve a problem on simple gas turbine efficiency. Okay, then based on this one we have to find out the efficiency of the reheating of gas turbine. Okay, here the simple gas turbine plant operating on Brayton cycle as air entering the compressor at 100 kilopascal. Okay, 100 kilopascal. P1 is equal to 100 kilopascal. It becomes 1 bar and 27 degrees centigrade plus 273. It becomes 300 degree Kelvin. The pressure ratio is 9. That is what P2 is equal to 9. Pressure ratio is 9 and the maximum cycle temperature is 727 degrees centigrade plus 273. It becomes 1000 degree Kelvin. That is what T3 is equal to 1000 degree Kelvin. Then what will be the percentage change in cycle efficiency and net work output if the expansion in the turbine is divided into two stages of each pressure is 3? Each pressure ratio is 3. This is very, very important thing. This ratio we are taken into account by solving the problem. With intermediate reheating to 727 degrees centigrade. Here reheating of gas turbine problem. This is the reheating of gas turbine problem. Okay, first we have to solve the problem by simple gas turbine. For a simple gas turbine, we have to write down the PV and TS diagram. This is what the PV and TS diagram of simple gas turbine cycle 1 to 2, 2 to 3, 3 to 4, and 4 to 1 to 2 isentropic compression, 2 to 3 constant pressure heat addition, 3 to 4 expansion, then 4 to 1 once again the cycle will be heat rejection. Once again the cycle which will be repeats will be taken place here. Okay, then based on the data we have to write down the data. T1 is equal to 300 degree Kelvin, P1 is equal to 1 bar, P2 is equal to 9 bar, T3 is equal to 1000 degree Kelvin. Then T2 is equal T2 divided by T1. Go to the process 1 to isentropic compression process. It becomes T2 divided by T1 is equal to P2 divided by P1 to the power of gamma minus 1 divided by gamma. It becomes T2 is equal to T1 into P2 divided by P1. That is, you can call as R, pressure ratio, R to the power of gamma minus 1 divided by gamma. T2 it becomes 562 degree Kelvin. Then T4 divided by T3 is equal to P3 divided by P4 to the power of gamma minus 1 divided by gamma is also equal to the 533.7 degree Kelvin. Then W net is equal to WT minus WC. That is what Cp into T3 minus T4 minus T2 minus T1. It becomes W net is equal to 205 kilojoules per kg. Then heat supplied QH is equal to Cp into T3 minus T2. It becomes 440.19 kilojoules per kg. Then cycle efficiency is equal to W net divided by QH. That is what 205 divided by 440.19. It becomes 46.6%. This is what simple gas turbine. This is the gas turbine. Once again reheating will be taken place. That is reheating of gas turbine to 727 degrees centigrade. When reheating gas turbine, we have to write down the PV and TS diagram. How it will be existing the PV and TS diagram. This is the way of writing the PV and TS diagram. Already we know this theory. We are based on that when we have to write down the TS diagram. 1 to 2, the expansion compression process. 2 to 3, constant pressure heat addition process. 3 to 4, the expansion. Once again, here in the reheating, it will be existing the two turbines, high pressure turbine and low pressure turbine. Okay, 3 to 4, the expansion. Once again, the heated reheater is there here, which will be reaching the same temperature. T3 is equal to T5, T4 is equal to T6. Here also we should write down here P2 is equal to P3, P4 is equal to P5, P1 is equal to P6. Like that only we have to write down the PV and TS diagram of reheating cycle. For T2 is equal to 562 degree Kelvin. We have to write down P3 dot pressure ratio. I have told this is what the pressure ratio they are mentioned in the problem. P3 dot by P4 and P5 dot by P6 is equal to 3. Then P4 is equal to P5. Then we have to write down the temperature ratios based on the process 3 to 4. T4 dot by T3 is equal to P3 dot by P4 to the power of gamma minus 1 by gamma. It becomes 730.6 degree Kelvin. T4 is also equal to the T6. Okay, once again you can calculate, you can get the same value of 730.6 degree Kelvin. Then we have to write down W net for a reheating gas turbine cycle. That reheating gas turbine cycle, which will be consisting of high pressure and low pressure turbine. That means WT1 plus WT2 minus WC. Then we have to write down Cp into T3 minus T4 plus Cp into T5 minus T6 minus Cp into T2 minus T1. Okay, then W net it becomes 278 kilojoules per kg. Then cycle efficiency is equal to W net divided by heat supplied. W net already we are calculated 278. Heat supplied will be taken here. The two stages the heating will be taken place because of the reheating of gas turbine. That is Cp into T3 minus T2 plus Cp into T5 minus T4 is equal to 39.1%. Okay, increasing of net work output. This is the efficiency what we are getting. Reheating gas turbine efficiency. Already we are calculated simple gas turbine efficiency is 46%. Just you can change of network output and efficiency. Just you can calculate here. Just you can observe here. Increasing the network output is equal to 278 minus 205 is a simple gas turbine work done divided by 205. It becomes 35.6%. Net work output it will be increases. What about the efficiency? Just you can observe here. The increase in the efficiency is equal to 39.1 minus 46.6. That is a 46.6 is a simple gas turbine efficiency. Then divided by 46.6 minus 0.16. That means that efficiency will be decreasing. The net work output is increasing. Negative sign which will be indicates the decreasing the thermal efficiency while during the reheating gas turbine cycle. Okay, this is what this thermal efficiency will be minus 0.16. Net work output will be increases, the efficiency will be decreases. This is all about a simple problem on. We have to solve the problem on simple gas turbine based on we are compared with the reheating gas turbine cycle. Okay, next class I will we have to solve 3 or 4 problems based on the different condition based on the problems. Okay, now I'll stop it here.